In this video, I wanted to offer a little bit more clarification about working with a scalar versus vector projection, and then give a couple of examples of when you would want to use one versus the other. So let's kind of start by maybe just looking back at the beginning of where this idea of projection comes from. So given two vectors, A and B, we find the projection of A onto B with the formula A dotted with B divided by the length of B, and then times B divided by the length of B. Okay, so I mean, we have a formula that's all well and good, but let's kind of look at what the idea behind this is. So if we want to draw a picture of this, suppose this is our vector A, this is our vector B. We can think about the projection as being kind of like the shadow that A casts down onto B, like this right here. So it's the segment of B that A has in common with B. And this right here gives us this vector, this whole thing. And the whole expression. This piece right here is the length of that vector. And this piece right here gives us the direction. Because, I mean, the idea behind this is that we have the dot product of A in the direction of B. So we have how much A has in common with that direction, and then pointing it into the direction of B by multiplying it by this unit vector that goes in the direction of B. So this entire expression right here is a vector, as we've said, and is called the projection. Or we can specify and say that it is the vector projection. Okay. And this is of A onto B. But we also have this idea of the scalar projection, which is really just the length of this guy right here. So if we only look at this first term, or this first piece right here, the length that gets multiplied in, A dotted with B divided by the length of B, without having B make a second appearance over here, this is just the length of the projection. And it is just a number, so it is called the scalar projection. Okay, so we've got these two pieces here. The length is given by what's here in front, and then we combine it with this unit vector here, and we get the whole vector there. So let's look at an example of breaking maybe down some more concrete vectors. So in this example, we are going to find the scalar projection and the vector projection of A equal to 3, -1 onto B equal to 2, 7. So projection formula. That's the A dotted with B divided by the length of B times B divided by the length of B. Okay, so again, the whole thing is the vector projection. And this piece here in front gives us our scalar projection. So we're actually going to find the scalar projection along the way of getting the vector projection. All right, so first things first, I think I'm actually going to go ahead and calculate the length of B here. So this is just equal to the square root of 4 plus 49, which is root 53. And now I'm ready to just start plugging numbers into my equation here. So I'll have 3, -1, dotted with 1 over root 53, times 2, 7. And then all of that is times 1 over root 53 times 2, 7. Okay, so I'm going to start simplifying it down, and then I'm going to pull out the individual pieces here. So we'll have 1 over root 53 times the dot product of these guys here. So that's, we're going to have 6 minus 7. And then this is still times 1 over root 53 to 7. This is a 7 here. Notice that I'm keeping this root 53 separate, tied to the vector B here and away from this root 53, and that's because the scalar projection only includes one of those normalized vectors B. So this piece right here with one of the root 53s is our scalar projection, and that is just equal to -1 over root 53. And then if we simplify everything else down, this whole thing here is going to give us 1 over 53, or yeah, 1 over 53. And then that should be negative there, and times the vector 2, 7. So this is our vector projection. Okay, so they're very similar, same idea, very closely related. The main difference, though, is just that the scalar projection is really only taking the length of the overall process, or the overall vector, and then the vector projection is actually the entire vector here. So let's apply this in another example. One place that it pops up that it's advantageous to use the scalar projection versus the vector projection is when we're trying to find, say, for example, the distance between a point and a plane. And that's actually going to be our next example here. So we will find the shortest distance from a point P equals -1 to 5 to the plane 3x minus 2y plus z is equal to 4. So in order to approach this problem the best, we're going to start by drawing a picture just to get an idea of what we're looking at and kind of help us figure out where we need to, how we need to apply these things. So if this is our plane here and this is our point P, so we want to know the distance between P and this plane. Well, intuitively, the shortest distance between P and this plane would be to just kind of draw a straight line from P that goes directly down to the plane. And this line here, we would really probably want it to form a right angle in order to get the shortest distance, right? But this leg right here is kind of difficult to find directly. So we're going to kind of do it a little bit differently than just saying, okay, we're going to find the length of this segment here. What we're going to do is say, okay, here's a point Q that we can pick any point Q on the plane. And there's a vector between P and Q. And what we can do is figure out what part of this vector, how much of this vector points kind of in this up and down vertical direction here. And the way that we do that is by taking the projection of PQ onto a vector that points vertically away from the plane. Well, incidentally, that vector that points vertically away from the plane like this, that's going to be your normal vector, right? We can't just use the normal vector because it may not be the right length, but the projection of PQ onto that normal vector is the right length. And since we only care about the length, this is a case in which we want the scalar projection as opposed to the vector projection. All right, so that's what we're going to look for, is the scalar projection of a just a random vector that goes from P to the plane with the normal vector of the plane. And I mean, that's an equation that we have. That's just PQ dotted with N divided by its length, just like so. So that's going to be our scalar projection. So all we got to do is just fill in the pieces to be able to use this formula. Well, the normal vector we have here, that's provided in the equation of this plane, that's going to be 3, -2, 1, and its length is equal to the square root of, well, 9 plus 4 plus 1, that's just equal to root 14. Okay? So now we need to get PQ. We first have to choose our point Q. It can be any point on the plane, which means that it can be any point X, Y, Z that satisfies the 3x minus 2y plus z equals 4. When you're working with these kind of problems, the easiest thing to do is to plug 0 into 2 of these and then figure out what the other one has to be. We're going to use Q equals 0, 0, 4 in this case, because that's pretty straightforward. So what this means then is that PQ is equal to positive 1, -2, and then -1, just like so. All right, so I think we're ready to actually compute our scalar projection PQ dotted with n divided by the length of n. So PQ is 1, -2, -1. Dot that with 1 over root 14 times 3, -2, 1. And we are going to get, I like to pull the root 14 out to the front. 3 plus 4 minus 1, which is equal to 6 over root 14. So what this means then, since this is the scalar projection of PQ onto the normal vector, which just gives us the length of this leg right here, this guy is our distance. So this is an example of when you would want to use scalar projection, because we only care about the length. We don't really care quite as much about the vector itself. However, I will say that you can just find the vector projection and then just take the length of that, but it's just a little bit of extra work there. So in this example, we're going to use the vector projection this time instead of the scalar projection to be able to find an orthogonal decomposition. So specifically, we're going to find the decomposition A equals A with parallel part plus A perp for A equals -3, 2. And we're going to do this with respect to B equals 4, 1. So just to kind of recall the idea of this orthogonal decomposition, if we want to look at our vector A, like so, and suppose our vector B looks like this. So A is kind of hovering over B. A has that projection down onto B like this. Think of it as like the shadow. And this vector here, we can think of it as the parallel part of A with respect to B. So this right here, this vector, since what we're looking for is the vector, this is the vector projection, and that's just equal to A dot B divided by the norm of B times b divided by the norm of b. So that part we know how to find. But after we find this parallel part here, there's a second component left over that is perpendicular to b. And that's just found by taking a minus the part that's parallel to b. Okay, so this creates kind of like this orthogonal decomposition where we have the piece of a that points in the same direction as b and the piece of a that is orthogonal or perpendicular to b. And to do this, we just walk through the vector projection formula for the first part, and then to get to the other piece, we just subtract it off from a. So let's find our parallel part. This is equal to a dot b divided by the length of b. Which is equal to -3, 2, dotted with, oh, we need the length of b. Length of b is equal to, it looks like it'll be root 17. 4 squared is 16 plus 1 is 17. So 1 over root 17. And then that's going to be multiplied by our vector b, 4, 1. And then we have the vector 4, 1 divided by root 17, like so. Okay, so to do this dot product, I like to pull the 1 over root 17 out to the front. If you multiply that through before you do your dot product, you are just begging to make a mistake. So I strongly recommend that you pull it out to the front so we can deal with it later. So dot product of these two vectors, we'll have -3 times 4, so that's going to give me -12, and then we'll have plus 2. And then this is still times 1 over root 17 times 4, 1. All right, well, because we left the root 17 out here, we're able to just multiply this and this together. So we have 1 over 17, and actually this right here is going to give us -10, and then this is times 4, 1, which I guess if I want, I can rewrite that as, so that's my A parallel, is equal to -40 over 17 and then -10 over 17. Okay, great. So this is our parallel part. And now all we got to do is take this and subtract it off from A to get our perpendicular part. So this is just equal to, should have -3, 2 minus -40 over 17, -10 over 17. This winds up being equal to, I got -11 over 17, and then 44 over 17. So that's our A. So yeah, that's pretty much all that you have to find for these right here. And again, this is a case in which you want to use the vector projection because, or just the regular projection, and we also just simply call it projection, because we are actually this time caring about the direction that that projection is pointing as opposed to just knowing what the length of it is. So that's pretty much all there is to working with scalar versus vector projection. I hope that this was helpful.